Welcome to week 7 of the course. So the last two, section 5, the last two chapters of the course are on artificial intelligence and deep learning. So let me just quickly remind you of three of the main problems of artificial intelligence, and all of these problems get solved by deep learning. So number one would be the set of techniques to solve image processing problems. And of course, in the advent of the internet, social media, labeling photos, videos, searching photos, videos, such things is very important. Underlying this is a lot of hardware and software. So Intel has CPU chips, which are good at manipulating vectors. NVIDIA has GPU chips, graphics processing chips that are good at manipulating matrices. And you want to think of a photo or an image as a matrix. And then Google has something called a tensor processing unit, which is good at manipulating a tensor, or if you like to think of that as a three-dimensional matrix or a sequence of images or a sequence of photos, so aka a video. So there's a huge amount of effort put into software and hardware for designing chips. Even deep learning algorithms are now coded into chips. And the whole idea is, how do I very quickly manipulate videos, for example, in YouTube, and deliver these things as necessary. So one big class of models are image processing models, which we'll get to today. And then in the next lecture, we'll talk about two other major applications. One is natural language processing or speech recognition, or text analysis, or something called machine translation. And there's a couple of algorithms I want you to learn. One is Google's word2vec. So how do I take language and first of all convert it to a vector to numbers, because deep learning will be able to manipulate numbers for us. And then another algorithm that Google uses for its search called BERT. And then we'll also look at robotics or automation problems. There's something called Q-learning or reinforcement learning, which is really an old set of techniques due to Richard Bellman in the 1950s. For example, Amazon Web Services uses these things. There's also a class of problems called bandit problems that someone called John Gittings worked on theoretically in the 1970s, but with modern day computing, these things can be implemented in real time on large data sets. And as I said, maybe the key insight is that deep learning will solve all of these problems. So we'll also talk about the mathematics and algorithmic properties of deep learning. Okay, so hopefully you've been reading along in the AIQ book. So remember, there are 7 chapters there, and you can see how they match up to the AI chapters that we're going to be talking about in the next couple of lectures. So remember, chapter 1 was Bayesian personalization. Chapter 2 is the image processing. So if you want to go back and read chapter 2, you'll learn a lot about image processing. Chapter 3 is about robotics. Chapter 4 is about natural language processing. So those two are next time. Chapter 5 is about real-time monitoring and decision making. And then a bunch of applications. Chapter 6 is healthcare analytics, and chapter 7 is sports analytics and big data. Okay, so just a very quick recap. What does AI really mean? Well, to us, it's really just an algorithm, or really a sequence of algorithms put together. So the nice thing is that you can piece together, for example, an image processing algorithm with a natural language processing algorithm to label photos or label videos, for example. And remember that algorithms really deal with probabilities rather than certainties, so that's where the probability piece of the course comes in. But of course, there's a big question of how do algorithms know exactly what to do, and that in some sense requires a model, or aka a deep learning algorithm. And really, one of the big insights of deep learning is that rather than build theoretical models, you can take very, very large empirical data sets and essentially pattern match. So we'll talk about that. There's a hyperlink down here. It would be remiss of me not to point out that with any new developing field, there's been a lot of AI failures. These models and algorithms are designed by humans, and lots of things still need to be ironed out. So it's still a very exciting area to work in. still lots of opportunity for things to be done. And again, one of the big differences between, say, machine learning and sort of old school traditional statistics is the machine learning approach is really a predictive analytics approach. Really, we're just interested in finding a predictive rule, not so much the estimation side or the causation side of things. And prediction can actually be or pattern matching can be solved quite cleverly by these deep learning algorithms. So in AI, what do I mean really by a pattern? It's a prediction rule mapping an input to expected output. So if I see a photo, can I label it as a cat or a dog, for example? And by learning a pattern, it just means finding a good prediction rule for a given data set. And as I said, these data sets have become huge. And if you have a good pattern matching technique, then you can actually come up with very powerful algorithms. Given an input, I can give you expected output. And sometimes I'll call prediction rules models, and sometimes I'll cause the process of using data to find a good prediction rule, training the model. On another couple of topics that people are always interested in is will automation, how far will these prediction rules go in terms of helping mankind? And really the whole goal of the AIQ book was to show that when humans and machines interact together, it can be quite powerful. And so the democratization of these rules is hopefully a useful thing. But of course, humans develop these things, and better to develop these things for the human good. So, and also better for humans to understand what the power of these rules. So we'll talk a little bit more about that. So you'll see how powerful this paradigm is. And these are age-old questions. So this isn't a question that came up yesterday. For example, this hyperlink, the Turing hyperlink. In the 1940s, Alan Turing warned about robotics and algorithms coming to automate your job ages ago. So it's not as if this is an old question. Okay, so as you know, I like to do these sort of one-page examples. And one other thing I should say with all the examples that we're going to do in the next couple of weeks, I'm really just giving you an introduction, a flavor of what can be done. Every example you can go into a lot more detail, and a lot of time and human effort's gone into developing these fields. So again, they're age-old problems, and image processing, machine translation, and such problems have been around for since the beginning of time. So you're seeing the culmination of a lot of very hard work by a lot of very good people. So hopefully the next couple of weeks will give you a good introduction and get you excited about you looking more into the details of each of them. So one thing I thought was actually quite interesting. So pattern matching mammograms. Chapter 6 is what healthcare analytics. And I thought what was interesting about this is that there's a very nice NPR podcast that talks about how mammogram tests were initially found. And essentially it was found purely empirically by looking at data, right? People didn't really know what they were looking for, and humans sort of saw white blobs and things that didn't look quite right, and they managed to correlate that with cancer. So again, nowadays everything will be done by computers and deep learning, but some of the great scientific findings in the world today have just been done by empirically looking at data without any without any theory. So just finding empirical irregularities in data sets is still an interesting problem. Now, one problem dear to my heart is chess, and so we won't talk that much about it, but I'd like to give you an idea of this is more in the robotics section that we'll do next week. So I give you an introduction here, and we'll talk more in depth about how the modern computer algorithms solve chess. So remember that Claude Shannon is one of the founding fathers of AI and information theory, after von Neumann, one of the great pioneers. And what's interesting about chess is that a game of strategy that has an incredible number of possible combinations that you could never enumerate. So it's something called a Shannon number of a game. So 10 to the power 152 for chess. The other famous game is Go. I think that's about 10 to the power 900. So just a state space, or what's known as a state space, with an incredible number of possibilities. And the whole goal is, can I find a good decision rule? Can I optimize some criterion? So for example, in chess, it's just, how do I maximize my probability of winning? And there's a great website called chess.com. And, starting around about the 1980s, people sort of thought, oh, actually starting in the 1950s with Shannon himself and von Neumann, both of them were interested in how to code up chess, but really starting in vain in the 1980s, people tried to build computer models of chess. And there's lots of different ways you could think about doing it, right? So for example, you could take a data set on all games that have been played, you could categorize them into three different groups: as openings, as middle game, as end game, and you could try and sort of figure out what are good openings, good middle games, good end games, for example. Now, one of the first original algorithms took 23 million human games of highly rated players like masters and grandmasters, and basically just ran a logistic regression, so something we've already covered, and tried to predict what the next move that a grandmaster would do on a chessboard. And what's interesting was that you could, with a simple logistic regression, you could get to, with some what's known as hand-coded factors or hand-coded rules, things that you think might make a difference, like take pieces if you can take free pieces, if you can take loose pieces, checkmate if you can checkmate in one move. You've got to still search for checkmate, so sometimes not as easy to find checkmate in one or checkmate in two as you would think. So run a logistic regression on a data set of grandmaster games. And logistic regression was able to predict with 57% accuracy what a grandmaster would do. So already with a pretty simple AI model, you could do quite well. And in some sense, Deep Blue may be one of the more famous ones in the 1990s that ended up, I think, lost a game to Kasparov and then famously beat Kasparov. Was essentially based on this type of algorithm. And it wasn't until Google DeepMind and Demis Haspis, the person that owned Google DeepMind, who himself was a very good chess player, got somebody called David Silver, an English computer scientist that had an interest in game theory problems, who's a professor at University College London, until he got David Silver to code up what's known as reinforcement learning. So that's something that, again, we'll cover in the robotics chapter. And essentially, it's the coding up of something called Bellman's principle of optimality. So even though the mathematics was known around in the 1950s of how to solve these types of game theory problems, the computational power and abilities didn't really come until about 10 years ago. And that's partly because the state space is so big. Remember, Shannon number 10 to the power 152, lots of possible combinations. So the idea will be to give the algorithm an objective function, so for example, maximize the probability of winning, and then to build two things, and we'll build this with deep learning, of course. We'll build what's known as a value function. So if you're in the given state of the system, V of S just measures how valuable that state is to you if you act optimally in the going into the future. So that would just be a number from 0 to 1 and would assess what the computer thinks the current probability of winning is. And then something called a policy function. That would be, again, given a given state, what's my optimum pi function as a function of A, the possible action to take. So on a given state of the chessboard of all possible moves I could do, what's my best optimum action? And one of the interesting things is that we'll use two deep learning algorithms, one to model the value function and one to model the policy function, and they'll sort of interact with each other to build an overall decision rule for how to play chess. And again, one of the current algorithms is this AlphaGo 0 that we'll talk about. Okay. Very quickly, again, this is the old school way of looking at a chessboard. You'd look at a position. I'm going to call this a state of the system. So what white has a king, a rook, and a bishop, and black just has a king and a rook. And from this, you want to work out a value function. So given the position on the board, one approach that people used to do they would value pieces. So 1 for a pawn, 3 for a bishop, 5 for a rook, 9 for a queen, 3 for a knight. And from this, you'd work out the value of the state for for white. And you'd see that, very simply, essentially, white is up a bishop. So he's plus 3 points. But of course, this doesn't really take into account what's known as conditional information. So it's not really Bayesian. In some sense, this value vector here is like a marginal vector. It's telling you on average over all possible games, how much is a rook worth to you? 5 points, for example. Well, depending on the spatial position of the board, so depending on the state of the board, in some sense, these values will change quite dramatically, right? So really the big insight of AlphaGo is not to value pieces, 1, 3, 5 that you're taught when you learn chess, but it's to look at the position of the board S and to somehow dynamically value these pieces. And of course, the goal is an objective to maximize the probability of winning. So rather interestingly, the old school approach of looking at marginal unconditional information, clearly is not optimum when you can incorporate spatial information and value the pieces locally for a given state S. Excuse me. Okay, and another thing that I think if you can see the slide carefully is just became very popular a year or so ago when Netflix came out with the Queen's Gambit series. There's a link down here to the last game. I think Kasparov advised people on the game, so it's true to chess. And Queen's Gambit is actually one of the good openings for white. So if you look at the openings that AlphaGo will pick, it'll like the Queen's Gambit. And I thought it'd be interesting just to show you that Anatoly Karpov, who was world champion for over 10 years in the 70s and beginning of the 80s, was a bit of an expert at the Queen's Gambit. And you can see that he basically won or drew every game, right? So essentially never lost when he played. Queen's Gambit declined over that long period. Okay, so hopefully that's a little bit of an introduction. As I said, I think one of the great advances, and I think, even though it occurred maybe about 10 years ago, because of the computational power and the algorithms behind it, I still think that, there's many years to go, and there's lots of interesting problems to be solved with deep learning, and it's become this tool that is solving basically all of these problems. So maybe the most widely used, or at least will be in 4 or 5 years' time, is maybe the most widely used machine learning tool for these so-called high-dimensional input-output problems. So image processing, speech recognition, things like driverless cars, are now all solved. Search algorithms are now all being replaced by deep learners. And really the applications are endless. And I always come back to a famous quote of John von Neumann, where he said, "Sir, you complain a machine can't do something. If you can define the task, I can build a machine to do it." So remember that von Neumann built one of the first computers. I think it was called Maniac, and also coded it up to play chess. So that was one of his original motivations, but with a goal to code up lots of other things. So these problems are interesting problems. And really, the simple way to think about it is deep learning recovers patterns. And one of the interesting applications down here, so this really wasn't solved till about 2015, was to take an image and then to the computer to actually describe that image. So again, as I was trying to tell you, that there's one of the nice things about these algorithms is you can mix them together, right? So you can have an image processing algorithm together with a natural language processing algorithm to try and describe the image. So this joint problem of image identification together with actually describing what's in the image purely by computer was one of the advances 5 or 6 years ago. And again, I'll super briefly touch on it, but there's a lot of matrix algebra and something called automatic differentiation to implement these algorithms quickly. So again, why do we care about deep learning? Hopefully you're getting the idea that one of the most important things to learn or appreciate what it can do. Well, one of the interesting things is that we talked about it already a little bit, is the input space X can be numerical. That would be the Intel CPU chips, or text, if I convert words to vectors, Or it can also be images, so like an NVIDIA GPU chip, or it can be a video like a Google TPU chip. So one of the great things that's useful about deep learning is that the input space can be extremely high dimensional. And along with that, it is a great set of techniques for manipulating data. So rather than sort of storage, or rather than just a computer language for manipulating stuff, in some sense this lies in the interface. How quickly can you manipulate tensors? So how quickly can you get YouTube to work and that type of problems? So you can see why it's got lots of so many business applications. Now, along with very high dimensional sets of data comes models with lots of parameters, and I've seen models up to 150 billion parameters in these deep learning models, and I'm sure they'll get bigger. Of course, the more parameters you have, the easier it is to do your pattern matching. So Alexa speech recognition, for example, or Google Waymo for driverless cars. And again, another interesting area is sort of standard data sets. There's something called ImageNet that's got about 14 million pictures in it. And again, the way you want to think about that is think of an image as essentially a matrix, but as a 256 by 256 image. So it's already 65,000 dimensions to begin with. And then on top of that, the number of different grayscale levels or colors that you're willing to add. So you can see pretty quickly that these problems would be very high dimensional. Again, something that statisticians used to work on, what's known as shallow models. So we wouldn't have many layers. We'd have one or two layers, but we'd have lots of variables or lots of what's known as nodes per layer. So we'd have what's known as very wide shallow models in things like non-parametric regression or these types of tools. But along came deep learning, and it decided that we'll have very sort of skinny and deep models. So we won't have too many parameters per layer, but we'll go down quite deeply. And of course, that gives you a lot of flexibility. You'll see in a minute, it's all about composing functions rather than adding functions, and that can give you a lot of flexibility in a high dimensional space. So for example, just think of modeling a house price. So Zillow, one of the great companies with a great data set and very good data scientists, you could have a bunch of possible inputs. There'd be some hidden layer or factors to learn from that. And from that, there'd be some price to calculate at the end of the day. And you could have multiple layers inside here, and the algorithm would figure out how to weight these things correctly. So what exactly is the value of school quality for a certain zip code, for example? So you sort of get the idea of input, what I'm going to call hidden layer, and output Y. Okay. So just a couple of slides on the mathematics of deep learning. It's really quite beautiful math. It's from a result in the 1950s by two Russian mathematicians, very famous mathematician Kolmogorov and his student Arnold. And I guess the way that I like to remember this is there are really no multivariate functions. Remember, I want to do a multivariate function because I've got a very high dimensional set of variables P. There's just superpositions or compositions of univariate ones. So if you let these little f functions be univariate, and they're called activation functions, and we'll take our favorite ones like tan h and ReLU, or the maximum function for an activation function, or the logit function, and then we'll take a univariate function and hit it with what's known as a semi-affine function. So just a weight matrix times some variables plus some offset b or intercept b. And then the trick to deep learning is, rather than having an additive model, is to have a model that composes functions. So one function becomes the input to the next function. In high dimensions, Kolmogorov-Arnold proved that this does the trick, that I can approximate any function by such a combination. If I delve in a little deeper, there'll be something called hidden layers. So if I let z be the first hidden layer as a function of the input x, you see z1 comes in here. The z's successively become arguments into the next function. So that's the composition. And again, I haven't been explicit, but really the trick here is dimension reduction. So X will be very high dimensional, Z will be lower dimensional, Z2 will be lower dimensional, like dot, 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 until I get to my prediction rule at the end of the day. And usually my prediction rule at the end of the day is really just a simple regression or simple logistic regression. So another way of thinking of deep learning is it's a very clever way of finding what features to put into a logistic regression or multivariable regression at the end of the day. So all this collapsing of layers is just a clever trick for finding features for running nonlinear regressions, and also finding out how to weight those features. What's important at different layers of my network. Okay, so I think that gives you a good idea of the mathematics behind deep learning. Let me just give you a little bit of an idea of what does it look like in high dimensional space. So really the competitors to deep learners are things called trees and something called random forest. Random forest is really just a combination of trees. So it looks like a blurred version of the tree. So remember, in a tree, I'm just cutting the X space up into little what's known as cylinder sets, so into little squares. And I'll look in here and I'll say, okay, what are my output variables in this square? And I'll do something simple like an average or something like a simple regression inside a square. So you can think of a tree model as essentially finding cylinder sets, and you can think of random forest as essentially doing a blurred version. Now, what does deep learning do? Well, deep learning puts an architecture in there, so it's more specific than just cylinder sets. And in some sense, it does hyperplanes rather than cylinder sets. So trees are really a special case of deep learning. So it's a much more complicated structure, and with that, you're able to pattern match a lot more interesting data sets. And again, if you want to become an expert at deep learning, you have to understand a little bit about what structure you put on. So there's things called recurrent neural nets or long short-term memory models. One of my favorites is this thing called an autoencoder, where the input and output are similar, and you find the hidden layer in between. So it's a little bit of effort of what architectures and structures do well for different problems. So in an LSTM model, sort of a new way of doing time series, you'll see people talk about different architectures, and you'll see pictures that look something like this. A one-to-one network would be a simple rule, many-to-one, or even many-to-many. And inside there'd be weights and activation functions. Okay, one more quick slide on a topic you need to realize that goes into these things. There's something called dropout. And all dropout is just a way essentially of doing variable selection. And it's sort of a blind stochastic search way of dropping out a whole bunch of variables. Remember, one of the problems of deep learning is that this input space is so high dimensional. You've got to have a clever way of cutting the dimensionality. And one way is just to randomly generate a set of Bernoulli random variables with probability p. So if p was a half, on average, you'd only be getting half the variables in that little step before you went and run it into a deep learner. So one of the interesting little tricks for doing variable selection is this thing called dropout. And if you look at the mathematics of it, it's very similar to something called ridge regression with a G-prior, which is something that Bayesian statisticians have used a lot to do these types of problems. So you'll see me add dropout steps at some stage. Excuse me. So again, very quickly, another network to learn is something called an autoencoder. So if I have a very high dimensional X, how do I in some sense crush it down? I use something called an autoencoder, and you'll see me talk about that in an example. Here's one I did with stocks. So you have the S&P 500 as input and S&P 500 as output. You might think that's a little strange. I can always predict the output from the input just by the identity map. But what's different here is I constrain myself to only having a few variables in the hidden layer. So in some sense, the hidden layer provides me with a more efficient portfolio, right? So if I wanted to do portfolio replication with the S&P, I might think of an autocoder architecture where I try and predict Y from X, but I force myself to have a hidden layer with a lot less variables. So, rather than buying all 500 stocks, maybe I just want to buy 50 stocks. What would be the best autoencoder representation of the S&P? So there'd be one possible applied example. Okay, excuse me. How do you play with these neural networks? Well, there's a nice website. If you go to the link, the two main computer programs are PyTorch and TensorFlow. And the idea is you get given an image, so like a curly image of dots, and you somehow have to pattern match that. And it gives you the option of how many neurons, or just how many terms at each layer, or how many layers you have. And you just play around with the inputs here. You let the deep learning algorithm run, and you just see whether you can match the image. So a more serious example would be you put in a stop sign, and you want to say, okay, what type of architecture would model a stop sign for me? You'd run it through TensorFlow, and you'd find out, okay, I need 2 layers with 4 nodes and 7 nodes, and that would do a good job of pattern matching that picture. Okay, like another example of that, just to show the difference between trees. So this would be a trees approach, and this would be a DL approach. If I've got red dots and green dots, and I want to separate spirals, it's relatively easy when all the green dots are inside the red dots. I can do it relatively easy, but it gets much harder when I need to do my spirals. But in deep learning, it's just a 2-layer network with a tanh activation function. Oh, and just a quick little reminder, tanh will take lines and essentially bend them a little bit, right? So if I had a ReLU or a max activation function, I would just get hyperplanes. So here, maybe I won't match it exactly, but I've got my red region and green region to separate the two sets of points. Okay, so hopefully that gives you an idea that trees get more and more complicated. I've got to do finer and finer cuts, and it's harder and harder to find how to do that, as opposed to deep learning, which can universally, with that simple architecture, solve all problems. And as I said, this composition of functions, as the depth of the network gets bigger, the number of hyperplanes can grow exponentially, and so that's what gives you the added advantage. And again, as I said, that what's the difference between trees and deep learning? Deep learning is just slicing up the data set with hyperplanes, and then essentially looking at a weighted average estimator across estimates in each hyperplane. Okay, so again, hopefully that gives you some geometric interpretation of deep learning. Okay, so let's come to second half of today's talk. Let's talk about image processing and see what people have learned there. Okay, so as I said, there were many different ways of solving image processing problems, from modeling to different types of algorithms. Nowadays, most things are done with deep learning, and really there's a huge number of business applications. Although looking at faces, I'll do some sort of face type examples, or at least point you in that direction. When did people get serious about deep learning? Well, as I said, really one of the sort of hockey stick dates is really 2015. Back in 2011, this is an article from The Economist. These computer algorithms were really moderately bad at finding out whether this is a cheater or not. So denoising a cheater was a lot easier for a human to do than one of these off-the-shelf algorithms. And then around about 2015, as people started to implement deep learning, the computers just got better than humans at identifying images. So, and now you have these big databases with thousands and thousands of different possible images, and you can give them to humans and computers, and the computers will win every time. So, sort of interesting. Maybe the original example is a thing called the MNIST dataset. being able to read checks or people's digit handwriting. So it was a data set of numbers from 0 to 9. So it's really a multi-class classification problem. These things were solved by convolutional neural networks. And just to sort of show you sort of what the currency is in these types of things, or these very standard data sets, and people just keep on implementing them with their better and better algorithms. And around about 2015, people came up with very accurate algorithms for solving the MNIST data set. So remember that the error rate in sample is only about 0.2%. So 99.8% of the time they accurately identify what digits were sitting there. And if you wanted to just, again, it's just a pattern matching rule. So there's no causal or no easy explanation for what the hell's going on, other than you start with an input vector. So 2 to the power 10, you've got 10 possible digits. You've got an output vector, which is just 10 dimensional. How do I get from X to Y? Well, I have to shove it through a bunch of layers, drop out layers with a 50% probability of picking a variable. And the max function, which is the ReLU activation function. So it's just a pattern matching rule. You'll take the data set of MNIST 0s up to 9, and you'll estimate the weights and offsets. And there you go, you end up with a rule. Given an input, I get to predict an output. And rather than calling it logistic regression, people will write it as an optimization problem of something called optimizing cross-entropy negative log likelihood. So essentially similar to a logistic regression. What would it look like in R? There's a very nice library that people have written on Keras. There are plenty of books nowadays entitled with names like Deep Learning with Python. So if you load Keras, load the data, a little bit of data preparation. If you build the model, so what do I mean by build the model? Softmax for the output layer classification, those 2 ReLU layers that we had. Dropout rate, here I've got 0.4 and 0.3. I could do 0.5 and 0.5, see what happens. How many units, how many essentially regressive variables at each stage. So really it's a 5-line procedure for implementing a deep learning model. An outcomes and an output that will show you how many parameters or how many total number of parameters. You can optimize the model, so you give it cross entropy loss to optimize, and then you can give it a new set of data and predict what's in that test case data set. So here I gave it a 6, a 5, an 8, a 6, and a 4, and hey presto, it goes back and magically refines the data that you've put in. And again, remember training. What does it mean by training? So the number of iterates of the algorithm, I'm keeping on iterating using something called stochastic gradient descent to find the weight matrices, and I'm trying to get my error as low as possible. So remember the 0.23 was one of the winning error rates. So I'm trying to get my errors as low as possible. There's a training data set and a validation data set. In the validation data set, I'm just given the X's, I'm not given the Y's. So I would expect my model to be slightly worse on validation than on training. So that's the basic idea. Maybe the most famous example of image processing was on season 4, episode 4 of Silicon Valley. If you click on the YouTube link, if you've watched Silicon Valley, you'll all remember the hot dog, not hot dog example. So it's a great fun example to watch. So I recommend you look on hot dog, not hot dog. And again, if you look in the book, I think is it chapter 2 of AIQ, James and myself go over a bunch of very what seem like disparate examples, and you just realize that they're all sort of deep learning image processing examples. So all the way from cucumber sorting to looking at images in CERN on trying to find subatomic particles. And so I think, again, this is just, very, very typical of these AI algorithms and why they're so generically useful is that they're very agnostic about the type of input you give them. So they're just very, very good pattern matchers. So if you give them a very good data set, they'll generally come up with a very good prediction rule for you. I won't spend too much time on this one, but as I said, one of the famous examples, I think it's in the introduction to AIQ as well, is this Japanese farmer who replaced his mother by downloading TensorFlow and fitting a deep learning model to sort, I think, the 9 different types of cucumbers. So different prices for different qualities of cucumbers. And so his mother got replaced by a deep learning algorithm. And if you go to YouTube, you can actually see his algorithm automatically working in real time. So rather than his mother having to sit there and sort by hand 7,000 cucumbers as he picks them, it's all automated for him. So one of the interesting examples. Once in a while, you'll see adverts on TV. Microsoft has one where it talks about using AI to identify and protect snow leopards. So that's an interesting one. Lots of companies, so anything to do with facial recognition. So any, L'Oreal, Sephora, any of these companies are trying to use the power of image processing to help sell you things. So there's a link there to a L'Oreal example. Driverless car. Again, how do you identify what's on the road or what's happening? Can I decide between a car and a horse, for example? Well, again, you can take an image and run it through essentially a whole bunch of filters. So another way of thinking of deep learning, if you don't want to think in terms of the mathematics of superpositions of affine functions, you can think of them as a sequence of filters. So convolutional filter, ReLU convolutional filter. Pooling is if I take a little group in the image, maybe a 3x3 grid, I just replace everything by the max in that. So it's just a dimension reduction scheme. And you can see that you can build up many layers. So I have, maybe a 20-layer deep model to get to my final classification over here. So the input is a big training data set. The output is how accurately can I identify all these different things. And essentially I'm running that image through a sequence of 20 filters. So it's hard to figure out what each filter at each stage is doing, but it's clearly doing something to help you separate here. Remember that I give it the objective function to separate out these images. So it knows it wants to separate them. So it tries to figure out how to weight the different layers in between. And again, there's an art to building the networks. So, for example, you really wouldn't want to do a fully connected layer to identify, say, a picture of Albert Einstein, because it'd have so many hidden parameters, right? I have to do some form of dimension reduction. And again, as I said, one of the secrets of deep learning is shallow deep rather than wide and narrow architectures. So maybe I would do something like this. I'd be able to locally pick out different little bits of the image, for example. And maybe I'd also share parameters across different locations too. So again, these a little bit like kernel regression, convolutions with learned kernels. So it's a little bit of an art of not having a model that's too flexible because it's got too many parameters, having a model that does a good job of picking up the different types of images. And as I said, convolutional neural networks is the architectures to look at. I think I said something a few slides ago about one of the, actually I should really have GPU and TPU as the neural net processors. Essentially, I look at an image, I want to identify whether that's a border collie or not. Essentially, I look at image gradients and I essentially look to see where the image changes, and that helps me figure out what breed of animal it is. And again, a lot of this is just matrix manipulation. Remember, think of an image as a 256 by 256 grid, so already 65,526 parameters times number of grayscale. So you've got a very high dimensional input, and I somehow want to extract the information from that. So lots of interest in accelerated linear algebra and automatic differentiation to implement these things. Okay, so as I said, all of these examples you can go and study a lot more. There was a very interesting Wall Street Journal article about how China uses AI to teach its kids, and each kid is subjected to wearing a band that flashes red or green depending on whether they're concentrating on their mathematics homework or not. So one to look there. More disturbing ones. There's a big company in China called SenseFace that so maybe more disturbing is looking at pictures of people going to markets and trying to profile people. Again, look at that. The article does a much better job than me of explaining it. So again, you can look at these links sitting here. So lots of issues to discuss, and as I said, facial recognition has become incredibly powerful, and big databases have been collected, and the algorithms really are so good at identifying people and places. Another skincare example. I'll jump through that one. Here's an interesting website. If you click on the link up here, you have to figure out which person's real and which person's fake. I think the real person's on the right, fake person on the left. But again, I could be wrong. If you click on that site, it keeps on giving you. You can have a little bit of fun of trying to figure out whether you can guess it right or not. Actually, humans tend to be quite good at these things. So in previous classes, it's it's quite a challenge, but generally the class can get 90% correct. But it takes a little bit of effort to get used to. So humans are still quite good at it, but it's sort of a fun one to do. One of these models isn't true. I think it's the one in the middle. Again, I'm not 100% sure, but I think that's the fake person. Here's an interesting example. Again, click on the hyperlink. There was a high school teenager in Ohio, I think, that wrote a little bit of deep learning code to generate an image, to generate a painting. And 3 guys in France just downloaded his code for free from GitHub and just hit return. So it took less than a second. Printed out this horrible looking image, at least in my view, a horrible image, and then went to Sotheby's and sold it for 400 grand. And the high school kid that wrote the code got nothing. So you can see that yes, intellectual property rights, who owns what, lots of code is up on the web for free. Here's a rather interesting objective function, something called a generative adversarial network discriminator function, and a neural network function G. So there are lots of people have come up with lots of interesting types of architectures for images, but I thought you'd find that one interesting. The first digitally created piece of artwork at Sotheby's sold for 400,000. Actually, a slightly more serious example. Actually, a couple. There's a nice link here to maybe NVIDIA. Remember, NVIDIA does graphics chips mainly for gaming, and people have used those to implement deep learning for facial recognition. So if you click on that link, you'll see the incredible ability of these NVIDIA chips to generate images. Actually, one of my favorite examples is this one. Somebody in Holland took the 346 paintings of Rembrandt, fitted a deep neural network model to it, and then just hit return, and essentially started to randomly generate new Rembrandt pictures. So of these 4, one is false. And again, I think humans, once you've spent a little bit of time looking at computer generated images and non-computer ones, you can sort of tell. And so hopefully when you've all looked here, which one is fake, it turns out it's this one here. And it's partly because some of the lines are too exact, right? Sometimes, and maybe the mouth here doesn't quite look like a mouth, but on the face of it, it's quite incredible how the computer algorithm from a given data set, it didn't need that much data, just all of his possible paintings. I guess there's lots of different brush strokes and brush marks, so it's actually a more high-dimensional data set than you would have thought. This one here is the fake Rembrandt. And what came to my mind was simply the problem of what's the true value of Rembrandts. Does the fact that you can infinitely generate new Rembrandts raise the price of the true ones, or does it lower it? So yeah, it's an economics question that at the moment it seems to raise the price of these things. And I guess what NFTs have come out, and yes, I don't quite understand the market for these things, but it's interesting that nowadays you can generate an infinite number of possible Rembrandts for free, yet the price of the real ones go up. Well, as we'll see, it's not just images; it's also music. So here's a great website created by Google. Create music like Johann Sebastian Bach. So Bach had very sort of mathematically type ways he wrote songs. So Google did pattern matching there, and you can actually go and create your own Bach song, which is quite interesting. So it's a very interesting website to use. Just picking out patterns, and then letting you go in and create your own. So that's fun. A slightly more serious one is like identifying skin cancer. Uh, so really, with just your Apple iPhone, you can take a picture of your skin or your hand where you think you have a possible problem. And I think for what 2,000 different diseases, the Google algorithm can identify with very high accuracy whether you have skin cancer or not, and much better than 23 of the top Stanford dermatologists. So again, this is sort of something that's interesting, is that most humans, when they train at something, I guess the magic is at the Malcolm Gladwell rule is you take 10,000 hours to train. Uh, well, maybe the idea is that because deep learning can look at these big data sets, it can look at 130,000 images and fit a deep neural network. Really, human training is absolutely no match for deep learning and large data sets. So just like humans can't beat computers at chess now, humans aren't going to be able to beat computers at things like skin cancer diagnosis. Actually, another interesting, I think I have the example coming up, but looking at blood, basically, the algorithm can look much finer than the human eye can. So if you put a bit of blood sample under a human microscope, it's no match again to the fineness of a deep learning algorithm looking at that. So identifying whether somebody has malaria or something like that is again much better done by deep learning. So Google has a company called Verily that looks at Google Healthcare Analytics, and I'm sure in the next 10 years we'll see a lot more people doing those kinds of things. Another famous one that Google advertised was, or Google Verily advertised, was trying to understand heart disease from an eye scan. So rather than taking a blood test, I think one of the other diagnostics for looking at your health is to look at the back of your eye. I think that's where your capillary tubes are the smallest. So if you have any kind of problem in your blood system, that'll show up at the back of your eye. And so with a big data set of 300,000 patients, Google did a bunch of pattern matching of eye scans, and it was sort of incredible how quickly it could predict diseases that you had, diabetes, or could even predict the age at which it thought you were going to die. So, and in some sense, when you look at the back of the eye, you can see which eyes have are healthy and which ones are not so healthy. So, sort of an interesting use of machine learning. And again, just back to MRIs and other such stuff. There's a whole bunch of applications there. I won't spend too much time on these, but again, you can see how these applications, together with humans looking at, trying to interpret the output too. I would have thought there's something called Chester, looking at chest X-rays for lung cancer. There's something for looking at Gleason scores, prostate cancer, looking at samples of that, making diagnoses, looking at something called Kaplan-Meier curves, and trying to show that these machine learning algorithms are better at diagnosing healthcare than us humans are. So I thought you'd find that quite interesting. There's the Larry Ellison discussion of detecting cancer cells and looking at blood directly. So if you click on that link for the video, Larry Ellison, who runs Oracle, has a very compelling argument for why these algorithms are actually very useful. Okay, let me stop there, and next time we'll talk about natural language processing. I hope you enjoyed image processing and deep learning.